So I will move you guys right into this next chapter, stream processing with Kafka streams, which is really an exciting topic. And to let you know, I think that most of the work you will do in the future will mostly, you will be doing a lot of things with Kafka streams. And I don't know if I gave you this pipeline of things I've seen in the past, but put it this way. In the old days, we had like Java MapReduce. And we know that Google is the company that created what's called the GFS, the Google File System. Why? Because Google had a problem to solve. They had a whole bunch of commodity systems, and they needed a way to store the data without losing their data. So they came up with a way of storing data across a whole bunch of systems, distributed system. They call this the Google File System. So in about 2003, sometime around there, they released a paper to say, hey, look, this is how we do the GFS. And the same guy called Doug Cudden was at Yahoo at that time. So he took the ideas from the GFS and he used those ideas to create HDFS, the Hadoop distributed file system, right? And then so Google showed to say, look, when we have distributed collection of systems, this is how we spread data and store the data across those systems and how it replicates the data and how it handles failures and all of that. But it says, well, what about processing the data on those systems? So Google came up with something called MapReduce, I'll say MR. And in 2004, they released a paper, somewhere around 2004, they released a paper that showed them how they did the Google MapReduce. Well, guess what? Doug Cudden took those concepts from there and also created the Hadoop MapReduce, the way to process where mappers will work with these records, key value pairs, and produce data to the disk. And then it has this concept of reducers, which will come and collect those data from the mappers and then go ahead and do some kind of aggregation or some other reduce function. So Google was the first one to introduce those concepts. Now, why am I telling you this? Because when open source or HDFS and MapReduce and those things, you're processing, working with key value pairs, working with big data. But in those days, most people had to write programs in Java, right? So hardcore developers writing programs in Java to do MapReduce. So the only people that could take advantage of it was that. Then Facebook came along. Facebook said, hey, look, we have a lot of developers that are doing MySQL and stuff like that, and they're not Java experts. So let's create this high-level tool called Hive, where we can write SQL-like statement, right? Well, they can write SQL-like statement to be able to query the data on those systems in HDFS, right? So Facebook came up with this concept of Hive, and you write the SQL-like statement called the HiveQL. But what am I telling you this? Why am I telling you? Because look, high-level tools, because not many people wanted to write at a low level with this low-level abstraction. So if you did the Hive would then run a subset of Java programs under the hood. So that was okay for them. But then we say, well, MapReduce is pretty slow because when the mappers work, right, mappers have to write I/O to the hard drive. And I/O is pretty expensive. So what happened is there was another framework out there called Spark. And Spark came along, and with Spark, right, which was created by a guy out of Berkeley, it came out of the AMP labs in UC Berkeley, and his name is Mateus Zaharia. But Spark decided to say, look, instead of writing data to the disk, and after the mappers are done, what we're going to do is we're going to process the data in this area. It's like a JVM, but it's memory, right? We're going to process the data in this area called executor. And then we will be able to pull the data from the disk into memory and process the data in real time in memory. And we will use something, a very low level abstraction, something called the RDD, Resilient Distributed Data Set. So which means when I create something like a file, I want to represent a file, this will be an in-memory representation across all the nodes for the given file, whatever the file name is. And then when I process this file, Spark will pull the data from the disk into memory, and then the processing occurs in memory. And it does not write the output to the disk like MapReduce. What it does is it does something called the shuffle, where it will send the data across to other executors in memory, but it will send from memory to memory, and then it will eventually go through the reduce phase and produce a final output. But just an overview, but the whole point to this is working with this low-level processing, you have to use either Java or Scala, right? Initially, and then later on they added the Python API, but they went from a very low-level programming to say, look, now we have something that they developed called the data frames, and then something else called the data set API. The data set is just a strongly typed API. Data frame is not strongly typed. But this is higher level abstraction because they wanted people to get away from the lower level, working with just pure code, working with RDDs. And then eventually Spark said, wait a second, we want to take it even a step further. Let's add the Spark SQL, Spark SQL, right? But then now you can even do something called structure streaming, where you use SQL to process the data in Spark, to process data in real time. But in Spark, it's typically near real time, because I think even with structure streaming, you still have like 100 millisecond latency, sort of like still micro batching to some extent. But the whole point to this is there was a low level to begin with, and then they moved to a more higher level API, dataset and data frames, and then Spark SQL. Same thing happened in Java MapReduce, and the same thing in other frameworks as well. And if you know about this product called HBase in the Hadoop world, it's like a NoSQL key value store kind of thing. But HBase also, you could write using, it had some basic operations. You could get, put, set, but then use the Java API. But then over time, there's a project called Phoenix that basically uses SQL-like statement that will be able to access HBase, right? So what am I telling, why am I telling you this? I'm just showing you the trend. Right now, the low-level producer-consumer API you guys are learning is great, but the higher-level abstractions, like when you get to Kafka streams and the KSQL DB, is a natural trend that you see in industry all the time, and it is happening with Kafka. So at a very low level, you guys have learned about the producer API. We know how to serialize the data, go through serialization, partitioning, buffer, then it gets sent across the network. Then you also know about the consumer API. The consumer comes, subscribes to the topic, it pulls, it gets the data, it processes the data, it comes in the consumer group. Those are the very low level. You choose either Java, Scala, or you choose some other programming language and use the librd Kafka C library under the hood. But that's what we saw in chapters 3 and 4, right? Then you say, well, we're moving to a higher level abstraction, something called K-streams. Just like what I've seen with other infrastructures, with MapReduce, with Spark, it is no difference here. So K-streams, what does that mean? We have a higher level, what they call DSL, domain-specific language, right? It's very much like the syntax like Java 8. It's like the streams API in Java 8, streams API. In other words, if you're familiar with the Lambda expressions in Java 8, where you can do stuff like map, flat map, filter, and all those kinds of things, this is Lambda expression, then the DSL becomes very easy. So you may be able to write 20 lines of code using a DSL that's equivalent to maybe writing maybe 200 lines of code or 250 lines of somewhere here. So no wonder Kafka streams is very, very, very powerful, higher level abstraction. Then you say, okay, well, even with that, we still have a higher level. And this is where the KSQL DB comes in, KSQL, right? KSQL DB, because now you actually have SQL statements where you can do select, star, whatever you want to do, SQL-like statements. but it's not NC SQL. This is just called KSQL, but the whole infrastructure is called KSQL DB. You write your programs using SQL-like statement, and it actually compiles to Kafka Streams application. So basically, the same higher level abstractions that we've seen with all other platforms. Guess what? You're not going to win this battle if you say, oh, I only want to use producer consumer API, because I've seen this before. So we will talk about when to use one versus the other. But the bottom line is it's here to stay, and it's very powerful. Now I see a question said, so this is like functional programming. Yeah, the DSL is very much like using the Streams API in Java. So if you're familiar with Java 8, then when you get to the Streams API, you'll see that there's methods in there that makes it very easy to do joins. For example, with a few lines of code, I can join two top, I can do a join between a stream and a topic and something very simple. Whereas it would take me so long to do that in the consumer code. So just to let you know, this is here to stay. So I wanted to tell you why I see this as being very important to begin with. And we're going to do stream processing, real-time processing, but it's here to stay. So it's something that I would say, after this chapter, you will have a good idea of what it's all about. But just to let you know that you can also take, I'm not trying to sell you something, but we do offer a 3-day course that also covers more depth. So in this chapter, we will be comparing streams to tables, and we'll be talking about the streams like properties and what is core partitioning. And then we'll be talking about the DSL, domain specific language. So after this chapter, you basically understand what Kafka streams are. So you basically write an application to process the data in real time as you would do from a consumer. But this Kafka streams program you'll see has both a producer and consumer. So let's look at what this means, right? It's just a library. You don't need to learn how a specific framework works, none of that stuff. It's just a Java client library, right? You can use it to do, build microservices or whatever you want. And if you're a Java developer, you are already familiar with importing libraries in your code. So this is going to be no surprise to you, right? You can run it in containers, in virtual machines, or on a bare metal system, or in the cloud, wherever you want to run it. And of course, it's powered by Kafka. In other words, you cannot have anything in Kafka without the Kafka brokers. This is something I hope you remember from this class. So you must have the brokers. To have anything in Kafka, I need to have the brokers, because the brokers is the true source of where all the logs are going to, all the events are going to be written to these brokers. Once I have my brokers, that's the core of my Kafka cluster. Then I can say, oh, I want to write streaming applications. I can import the library and I can create Kafka Streams applications. So let's say these are examples of Kafka Streams applications. And then they can all run together like consumers in the consumer groups, or they could run by themselves. And we'll talk about this a little bit later, right? One instance or several instances. But these Kafka Streams application will then read the data from Kafka, right? So they will consume the data from Kafka. They will do all kinds of transformations, change the data in their code, and then they will produce the data back to Kafka. So Kafka Streams application, what I want to show you, very important thing is they are consuming the data from Kafka and producing the data back to Kafka. So this is a very important point. But you cannot have Kafka Streams application without the brokers. You cannot have anything without the brokers. The brokers is a core of where all the data comes from. I'm sorry, what dry SRY is disconnected? Sorry, I don't understand that. Is Martin? Is that the question? Oh, yeah, I'm sorry. I think it's a typo, but I don't know what that means. Oh, I see. So someone got disconnected. I see. Did I get? Yeah, someone dropped and came back. I don't know why, but someone's disconnected. So Kafka Streams remember, it does not exist without the brokers. And then in the next one, it's perfect for small, medium, or large use cases, of course. Very powerful, especially when you're creating microservices, right? And it's fully integrated with whatever security we can use in Kafka. It's Kafka Streams can make use of it. And also, it can do exactly once processing, which we'll talk about just a little bit tomorrow. Exactly once processing, where you can basically do it like in a database. So in Kafka, it was long thought that a distributed system would never be able to do exactly once processing, but in Kafka, you can do that. And remember, it's part of the Apache core. So you can get strings processing with Apache. So this is real-time processing, right? And let's go on to this. So what do you use the Streams API for? Again, anything that you would think about doing, but you can do transformations and you can do joins. Whenever people say enrich, people have two different, table or stream or whatever, and I'm going to enrich, do a join on the data. And it's per record stream processing, millisecond latency. And we'll talk about what stateful and stateless means coming up in just a second. And it does what's called windowing operations. So I'll talk about that as well, what windowing means. Okay, but first I have to talk about what a stream and a table is, then I'll come back to that. It has all the buzzwords, fault tolerant and distributed. But as I mentioned, it uses a DSL domain specific language, which is very similar to Java 8. So if you're familiar with Java 8 or other functional programming language like Scala, you'll be right at home with DSL, right? So because it's very similar to those. So if you're familiar with any functional language like Scala or Java 8 Lambda expressions, you will be right at home. So just know that is, again, there's a lower level API called the processor API that can give you more control over what you want to do. But every step of the way, you have to define all your actions like your processors, your state store. And if you're not familiar with it right now, don't worry so much about it, but just know that there's a lower level API called the processor API that gives you more control when you're working in Kafka streams. So, and if you're a decent developer or if you're familiar with Java 8, then Kafka Streams Library is the way to go. If you're not familiar with Java, because when you want to do streaming, someone says, well, what are the choices if I want to do with Kafka Streams? And the only choice you have for Kafka Streams is to do Java or Scala, Scala. We do not give you choice of any other languages. So if you do know Java or Scala, you cannot take advantage of the Kafka Streams API. But then what you can do is say, okay, well, if you know SQL, then you can use the KSQL DB. Because when you write your SQL-like statement, or whatever you write, it will be converted into a Kafka Streams application, a K-Streams application, right? So this is, again, very, very powerful. And it's a Kafka Streams provides stream processing capabilities. There's other frameworks out there like Flink, Spark. So Spark is one of the popular ones. Flink is also popular. Not so much Storm and Samza as much anymore, but you will hear a lot about Spark and Flink in industry. And those are heavy frameworks. Like if you work with Spark, you require lots of memory for your worker nodes and JVM, your executors. So you have to understand the resource manager. And there's a higher learning curve to using Spark. Although it's gotten a little bit easier over the years with the new structure streaming, where you can use SQL to essentially do streaming in Spark. Okay, so streaming is processing data in real time, but Spark still does, it still has some latency. It has like 100 millisecond, whereas Kafka can do, again, record by record process all the data with very, very low latency, milliseconds. Now, Kafka Streams, I said, does not require separate resource management technology, just a library, runs on a separate number of machines. You do not typically run it on your brokers in production, right? Just as a side note, remember, I can have one system here, and this is my host, whatever you call it, host X, and I can install Kafka, all of Kafka services on here. I can install the broker software, the schema registry, the connectors, the streams application, but this is not a production setup because it's on one system. So if that one system dies, it's not a good thing. So in production, you typically separate your brokers from all the other services. So these would be like 3 brokers, and then I would have other services, other containers or whatever that would run, like my connectors, other containers or whatever I have here that would maybe run my KSQL DB server, right? And those all feed off the data from the brokers. So just know that it's very important, right? So let's go on to the next one. Why not just build your own? Well, because this framework is there, it's tested, it's very powerful, right? It's much easier to use, well designed, as I say, powerful DSL, designed for scalability, designed for failure recovery, all the buzzwords that you can think of, right? So you will see that once you start playing with it, why would I want to use the producer consumer API if I can write 5 lines of code as opposed to writing 200 lines of code? So I'm a big fan of Kafka streams. If I have any spare time, this is where I would spend my time, right? So why not? So this is a lot of different reasons why not? It's very powerful. Okay? And then Kafka streams concepts. Now we want to talk about the concept. So first we need to talk about what a stream is. Let's think of a stream as an unbounded real-time flow of records, right? The stream is a whole bunch of records. We say, well, the question you probably will ask yourself, where are these records coming from? Can you guys tell me? I know I mentioned it before, but I just want to make sure everybody's with me. Where are the records coming from in this case? I say, think of a stream as an unbounded real-time flow of records. So where do you think the records are coming from? From the topic, absolutely, right? And now let me ask you guys another question, which you, of course, know. How is the records getting into the topic? I know you know this, but please humor me. From some kind of producer, right? Whether you're using the REST API or you're using Java, Java or Scala, or you're using some other client library, it's coming from some producer, some microservice producing data to a Kafka topic. And then once the data hits the topic, if you have a stream, it's almost like saying, hey, I'm listening to this topic. I'm going to just pull every time the record hits this topic. If I'm listening to that topic, then it gets pulled right into the stream. So the stream essentially is the reason you see the key value here is because whatever the record format is that enters the topic is what will come into your stream. And I will talk about this a little bit more because we'll show you once we get to the actual how you use the stream builder class. You'll see it's really simple. But for now, just know that the stream, whatever your stream is, the data is coming from a topic. So you don't notice to say you don't have to explicitly request new records. You just receive them. Once you have a stream, that is the stream application has a consumer and producer as part of it. So it will be able to consume the records from a topic, and we know how consumers do that. And then it will consume the record, bring it into its topology to be able to transform the records, and then it will produce the records back out to a topic. So the key important thing to know is that a stream is just all the records that are in your, whatever topic you have subscribed to. If this record comes in, let's say I have a record coming to this topic and the record says customer 1. And then let's say maybe the customer bought some item for, the sales price is, let's say 70, what the sales of that item is. So I have the customer ID and then the price of the item that they pay for. So as the records come in, some producer is producing this to this topic. So here's another customer 2 and they pay $80 here for this. Here's another customer 3. So as the records are coming into this topic, if I have already told Kafka to, hey, I want to, create a stream on this topic, then these records will be coming into my stream. So my stream will have the records like customer 1 and the value 70. That's where we're looking at the key value pairs, the data that is coming to my streaming application, to my Kafka Streams application. So we'll see this in more detail, but this is the stream of events. As the event enters this topic, it will come directly into my stream. Customer 280 coming directly to my stream. It's this event. As it enters, then it comes directly into my topic. So essentially, what's in your stream is exactly what's entering the topic, right? As it comes in, another record comes in, customer 475. Sure, then right away it comes into my stream, customer 475, and available for processing in my application. So a stream, this sequence of events, is never ending because as the producers are sending data to this topic, right away it's coming into my streaming application. And we'll look at more of we'll look at how it works in the API. First, at a high level, I just like to print this picture because you don't have to know much to remember this part. And then it's okay, well, then what is a table? A table is sort of like the materialized view of the stream. Think of what we discussed when we talked about compacted topic, right? So in this case, imagine I have these streams of events. This user with account, the user account A is the key and the value here, like a deposit of $11.50. And then the user account A has another transaction minus 250. So if you look at that, that means there's only $9 left. And then account A again has $1. So now the total is 10. But these are all the events that are happening like that. So users using the bank ATM or whatever the user is doing, transaction buying items in the store, right? That's what's going on. And then, so how did it get into the stream? Because those events are coming to some user transaction topic. The events are coming to the topic where account A has a value of 1150. And as it enters the topic, then it enters your stream right away. So if you have a stream builder, if you are listening to this topic, then as the record enters, as soon as it enters here, it becomes available to your stream. You know, it's part of your, so that's what your stream really is. Then you say, well, what is a table then? A table is like the materialized view. So if you look at this example, if we took a table version of this, it says, look, we just want for a given key, like account A, we want only the latest value. So, but the latest value here, because these were transactions going on, 1150 minus 250, that's $9 plus $1. So it's $10. But let me give you another view of this, okay? To use the same example I used when I talked about compaction. But let's just pretend, here's my topic, and all of you guys have purchased stuff on Amazon before, or you have purchased from, and you have had delivery somewhere, or maybe from some online store. And so let's just pretend that the store has a topic. Let's just call it the sales topic, sales. And, or let's just sales delivery. This is the topic, sales delivery. And actually, I should have a better name for that. In other words, tracking, I'll call this tracking. Okay? This is a topic called tracking. Tracking. So that's the topic called tracking. So for a given product, let's say the product has a product ID 1 is now in New York City. Then product ID 5 is in California. Then another notice when the truck gets to, let's say product ID 5 comes in again and says, well, right now it is in Michigan. That's another update from whatever the tracking or delivery trucks. Then maybe product ID 1 comes in again, and now it's in Toronto. Okay. Then maybe this is product ID 7 comes in, and the product ID 7 is in, let's say, Ohio. And then you see product ID 1 again, and I'm almost done now. Let's say product ID 1 is now in Montreal. So this is the stream, this is the data coming into the topic. Producers are sending update to this tracking topic. Then if I create a stream on this topic, the stream is going to look pretty much exactly like this, right? There will be a stream of all the events with each one of these records in the stream. So the stream is going to look just like these events. But then what is the table going to look like? So the table is going to be like the materialized view of the stream. So for giving key, I want only the latest value. And so maybe it's now the product has been delivered. So when I look at product ID 1, product ID 1 was in New York City. And let's say where did it occur? Yet again, product ID 1 again is in Toronto. But the latest arrival is product ID 1 is now Montreal. So for table, you will have PID product with ID 1 would now be Montreal. And then the product ID 5 is in California, and then it goes to Michigan, and then we don't see it again, right? So the latest for the product with ID 5 is in Michigan, because that was the latest one year for ID5. And then the only one that's left is product ID7. ID7 is just in Ohio. So product ID7 is in Ohio. So this is what the table will look like. It's just like saying, right? It's like if the record doesn't exist, it's an insert. And if the record does exist, it's an update. So the table says for given key, if this is the key on the left-hand side, right? I want the latest value associated with it. So this is what a table is. Do you guys have any questions about that? Because if you don't, then we're good to go. I'm going to look into chat. So table represents sort of the materialized view of the stream. Any questions about that? Looking into chat. Acts, there must be at least one. Yeah. Okay, so first, yeah, we're going to talk about this table and talk about where you store the data for table coming up in just a second. But this table is it's part of like your code. Think of it as when you're writing your code, you have a choice. I can say create a stream or create a table. I can go from table to stream, from stream to table. It's all part of your code, but then it does have data that it can store. In other words, when you're working with the table, maybe you want to be able to do aggregations or store the data, and you can. We'll talk about the state store coming up in just a little bit and how you stored it in Kafka. But for now, I would say this. Do you know what a stream is? I'm looking into chat, guys. I want you to be comfortable. Do you feel comfortable what a stream is? Everybody? Okay. Now, next question. Do you know feel comfortable what a table is? You don't have to know all the details of the table, but do you know what a table is? Okay. Well, I'll be careful with the compilation of the stream, but it's just think of it this way. When you have a stream of events, the table is basically saying, look, I'm looking at the stream and I'm looking for a given key. I want the latest value associated with it, right? And we'll see actually this next picture here is what clarifies. This picture will clarify it. So if you look at this picture, imagine that you have temperature, you have sensor readings around around the whole city. And these are maybe along the beach, like those temperature or like those parking meters, right? And they are taking temperature. They have temperature sensors, and you hook them up. They have IoT, devices, and you're basically bringing them into Kafka and putting them in a topic, and the topic is called, let's say, temperature topic. So you have a producer collecting the temperature readings, bringing it into the temperature topic. And then from this temperature topic, you have a stream that is reading the data from this temperature topic, right? And so every time the record comes into the temperature topic like this, at offset 0, then that record is like the first one here in your stream. But another record comes in at offset 1, then that's where we have the right. Another record, a reading comes in from another offset 2. So you see, so the station ID is the key, and the temperature is the value. So when the record comes in to the topic, of course, if I have a stream listening to it, then it brings that in, and there's the first one. So then look at the table. The table representation of this data, since it's the first record, first time we see this key, station 1, so it's like an insert. So station 1 and the value. Then the next record comes in, right? And it's also coming to my stream, but then it says, okay, what is the table representation of that? Notice this one is station 5. So the station 5, and it has a temperature. So it's the first time we see station 5, so it's an insert, literally. And then station 3 comes in. It's the first time we see station 3, so it's like an insert. But then look, station 5 then sends another update, another reading from station 5. Well, we had station 5 before, so this time it's become like an update instead of an insert. So the temperature reading was 13.7. So now the table says for given key, which is station 5, I want only the latest value. So it updates it to 15.6. And then station 1 comes in again. Well, we already have station 1. So this is a new reading for station 1. So this becomes the latest update for station one. So you see the table is always like revolving or evolving facts, right? The facts are coming from the stream. And then question says, there will be definition for stream processes, whether to aggregate. Yes, so we will, we'll understand that coming up in just a second. There's one show, we'll talk about some of those. So first things first, I'm sorry, I built on simplicity to begin with. So if you tell me you're now comfortable with what a stream and a table is, then we will move on to the next step to say, I think you guys are okay now what a stream is and what a table is, right? Okay, awesome. So thank you, gang. Acknowledge. So this is what it's, if you understand this page, you are good to go. So now let's go into more detail now. Well, this part is something that happens on the broker, right? So this is something that happens on the brokers. This is compaction that we talked about before, right? They're just trying to remind you that when we look at a table, it's pretty much just like a compaction, right? Except that compaction happens on the logs, where you have those log segments, and then you're looking at all the keys in all the different segments, and then you will build a new segment. And for that new segment, you say, I want the latest for given key. I want only the latest value. So I don't care about this K3 or this K3 or this K3 or this or any other K3 that is older in time. If this is the latest K3, that's the one I want. For a given key, I want only the latest value. So after compaction occurs on the brokers, you only have the latest value for a given key. So, but this seems very familiar, right? It's just how compaction topic, it's pretty much like the K table. So in Kafka streams, your K tables can be created from any kind of topic, but of course, right? Notice to say if the primary purpose of the topic is to materialize the K table, then the topic should have a compact retention policy. So in other words, if I'm using K tables in Kafka, and I know that I'm going to be reading data from a topic in Kafka, I may want that topic to definitely be a compacted topic. So remember, when you create the topic, you choose whether you want to just leave it as the default policy is to delete the data after some time, but you can choose to say, nope, I want to have compaction or compaction and delete. So this is important to know. But this is, remember, compaction happens on the brokers. We're just showing you that it's related to Kafka, to K table. Okay. So you said, well, what is this stream processing topology then? Yeah, we look at this, right? If you look at this carefully, notice they say stream processor. We will see that we will use a stream builder class, and we will be able to stream the data from some topic. So let's say I have a robo topic. Oops, sorry, just a second. Let's say I have a robo topic here, ROB or robo topic, and this topic has partitions P0, P1, P2. So we'll look in the API and see that I can use a stream builder class to instantiate the builder object. And then I can say, stream the data. I'll say builder.stream. And I say, look, I want you to stream the data from this robo topic. So what's going to happen is Kafka will bring this data in from this robo topic into my Kafka streams application. And this topology here is showing that the data will come in through the source processor, source processor, right? And then once the data comes into the source processor, it's streamed to another node where this is where some transformation will occur. When you think of transforming the data, let me tell you what I'm talking about. Imagine that you're reading letters from these partition A, B, C. So I have the stream coming in, A, B, C. Stream of data coming in to my topic. It comes in, sure. And then, so let's say I now have A, B, C that's streaming. And when it gets to this point, I say, hey, look, I want you to lowercase, sorry if that's not so clear, lowercase all the data. So then now that's the transformation that will occur here. Then what's going to be streamed out is like lowercase a, b, c, or lowercase letter. And then when it gets to this point, I can say, okay, let's just pretend that I could say, give me just the first character. And then what's going to be leaving this one is just the letter A, right? So the whole point is you're bringing individual records from these topics, record by record, coming in into your source processor, and then you're streaming the data to your processing nodes. These are called processor nodes, but you see this on the stream processor, because this is where you'll be doing transformations. And then eventually you will write the output back to through your sync bus back to some topic in Kafka, not the same topic, but like another topic, robo out. But let's just say, I'm just making this up, but you write it back to a different topic in Kafka. So this should look very familiar to you guys, like it's what like a DAG, directed acyclical graph, right? And Shirley's saying, let's see, I'm sorry, I missed the questions there. Let me come up here for a second. Yeah, so the node represents another processor or thread. Now, notice that in Kafka streams, when we talk about this, like I said, it's like a DAG, directed acyclical graph, right? When we talk about the processor. So you have this concept of these nodes are the processor, and Sharon is saying, yeah, node is an operator in the stream. It is pretty much Java. Similar, it's just that this is where your transformation is going to occur, and we refer to it as a processor node, right? And where the data comes in, so your source processor is that type that it doesn't have any upstream processors, right? This is where the data is going to come into your topology. So you produce the data coming in, and then you'll be consuming, and we'll see that coming up in just a second. And the sync processor is the one that kicks it out, right? Does not have downstream processors. So, and then in between, these are what we call processing nodes where your transformations will occur. And that's what I just tell people to keep it simple. It's like I'm doing from one, and like the example that Shilin gave, like if I do a string and then a filter and then a map, this could be a series of transformations that are occurring. But we will see some of this coming up in just a second. So if you're familiar with DAG, directed acyclical graph from other frameworks, yep. No one stream does like the filter, one stream does the map, and yeah, so we'll see this example coming up. Every time you do it, you create a new stream as a transformation. And it's the result of the filter. Yep, so Shillin's right. Yeah, the result of filter is also stream, and you can apply another filter. That is absolutely correct. And then to say, so sync is the terminate. So sync, yeah, just think of the sync as to say, look, there's no further downstream processor from this. That's where it's going to then go out. Yep. And then the last part, someone says, to a string to the, oh yeah, okay, I see, you're familiar with that. And then the whole point to this is when you're processing the data, right, just know that you bring it in through your source processor, and eventually you will go out through the sync, and in between, you'll be doing transformations, and this will all make sense in just a second. Yeah. To Liz doesn't make sense in Kafka. Yeah. So in Kafka, when they say unbounded, the streams are never ending, right? So this is why, because I have the data that is constantly flowing, but this is why it's going to be very important to use a window, because we need to specify a border in time. Like when we want to do aggregations, we need to say between this time and this time, give me like all the login failures for all users that fail more than 5 times. You want to specify a border in time. And this is where we will talk about windows coming up in just a second. Good questions, guys, and good answers. Okay, so let me go to this next one now. This is a very important picture that talks about what the Kafka Streams application looks like. So look carefully. Let's have some fun with this one, okay? So look carefully. Notice that this Kafka Streams, this is your Kafka Streams application, right? It has a consumer and a producer. Notice here says stream thread 1, and this one says stream thread n. So if you notice carefully, I have a thread, and the thread has consumer and producer. If you look at, there's another thread, consumer, producer. But if you look in this one, notice this topic here that says input. There's a topic here that where the data will come from that you are bringing to your Kafka Streams application through your source topology. Notice you will be consuming from those partitions, bringing it into your topology, and then you'll be doing your processing, your map, your flat map, your filter, all those things. And if you have information to store, like state information, you would store it in this state store, what they call the state store. I'll talk a little bit more about that in a second. But the important thing to this picture to pay close attention to is that this topic here has 1, 2, 3, 4 partitions. You guys see that? And if you notice this example, this Kafka Streams application, it has something called a task right here. Task, 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 task. So what is that trying to say? Well, the number of tasks will be equal to the number of partitions. Very important concept. Okay. I can have one thread running a number of tasks. Or in this case, I have one thread running 2 tasks and another thread running 2 tasks, but the total number of partitions 4. So you have a total, still have 4 tasks. And each task, as you can see here, has its own state store. And if you notice carefully, each task is processing, a task is tied to like the partition data that is processing. So it's processing and storing the state, right? So each task has its own state store, right? And then Schilling says n threads, each thread, n tasks. So the consumer group under this stream application has m times n consumers. So it's a thread, let's say m times n consumer. So depending, yeah, I will break this down another way. You can have the degree of granularity has to do with the task. If I have one thread, I can have any number, I can have one thread or more, but the number of threads you have will directly be tied to the number of cores you have. Because if I don't have enough cores, I can choose whatever thread, and I may not definitely get that level of parallelism. So you tie the threads to cores, threads to cores. And if I have multiple cores, I can increase the number of threads I have, but you can have one thread, or you can have, in this case, I could have 4 threads. And each thread, so in this, there's a simple property that you could set in the Kafka Streams application to just say num stream threads. And if I know I have multiple cores in my box or in the whatever container VM that I'm running, I can say, okay, num stream threads equals, let's say, 6 or some 4, whatever. And then I can have, in this case, easily have 4 threads, and then each thread will run, could run 1 task, and I still have 4 tasks. Or I could have just 1 thread running of 4 tasks. But the key important thing is if you have 4 partitions, you will end up with 4 tasks. And that's the thing, very important to be aware of that. And your Kafka Streams application, this is your whole Kafka Streams application that has both the consumer and the producer as part of this application. So it's very, very, very important to feel comfortable with that. And then when you say, well, what is the state store? Each task has a state. Because sometimes when they talk about stateful processing, right? Let's say if I want to keep a count of how many times the shilling dropped out of the Zoom session today, right? I have to be able to store this data. It's like almost like a counter variable as you would in a program, but I have to keep track of it. So this is stateful information. If I don't keep track of it, then every time it happens, that's like will be like the first time, right? So the stateful information, I want to say like how many times this login failure occur over the last 5 minutes, but I need to keep track of it to be, and that's an example of stateful information. You store that in a state store. The state store by default is something called RocksDB, which was written in C++, and it was also created by Facebook, right? You can also swap that in. It's swappable. You can create your own in-memory key value store, use others, things that you want to use. But RocksDB is the default. And we'll talk a little bit more about that. But for now, let me ask you guys this question. See, it's a trick question. I don't expect you to know this, but we just want to have fun with this. So what if in this Kafka Streams application, this is one topic here, but we know that you have a consumer, so consumer can subscribe to multiple topics. Here's another topic. Imagine that this topic has 1, 2, 3, 4, 5, 6 partitions. And how many tasks do you see? How many tasks do you see? How many tasks do you think will start at this point? And I don't expect you to know, but it's interesting. Right? How many tasks do you guys think? I have 2 topics. Topic 1, topic 2. This one has 6 partitions. This one has 4 partitions. And I'm writing my Kafka Streams application. How many tasks do you guys think will start? And you don't have to be right, just for fun. I don't expect you to remember. Okay. And a lot of times that people would think that is 10. People would think that is, a certain number. But how many tasks? So in this case, okay, we're really enjoying the guess. Now, in this case, you will start the higher of the 2. So since this is 6 and this is 4, the first time I started working with Kafka, I actually thought it would be 10. But what Kafka Streams does is says, look, hey, this is 6, this is 4. I'm going to start 6 tasks. It picks the higher of the 2 partitions and it will start. So in this example, you would start 6 tasks because this topic has 6 partitions. This one has 4 partitions. So you pick the larger of the 2 and you start 6 tasks. But each task will have its own set of state store. And we'll talk a little bit more about the state store. Remember, it stores stateful information and it's very important. Then Gang said, why don't Kafka create 10 and each task will service 1 partition? Well, because, it's the 6 is enough. I know it's just optimized in that case, because with 6, I can have the same instances feeding from both of the 2 topics, and we will see some other reasons why that would be very useful, like when we talk about the co-partition. And because typically if both of the topics, correct, more towards optimization, exactly. So do you guys have any question? Yeah, 6 is enough, absolutely. And so it's optimized. It doesn't have to spin out 10. So 6 does the higher of the 2. Do you guys feel okay with this concept? So your Kafka Streams application, very important. Notice it has a consumer. Oops, sorry, my eraser. It has a consumer and it has a producer. And because of that, consumer and producer, then guess what? The consumer properties that you will be able to set. And also, guess what? There's producer properties that you'll be able to set in your Kafka Streams application, right? And that should hopefully make sense. So I have a consumer and a producer. So I'll be able to set consumer properties and producer properties in my Kafka Streams application. I'll be able to bring the data in, and we'll see that coming up in just a second. So this is actually a lot of fun, right? So let's go on to this one. So Kafka Streams application architecture. Now, if you look at this picture carefully, right? This is just a library, and we'll tell you this in the notes. But we have all the features built into Kafka Streams application. Fault tolerance is scalable. It's this, in other words, you could do a lot with this, right? It has all the buzzwords. Now, the important thing to know about Kafka Streams application as well, notice this is like app instance 1, app instance 2, app instance 3. Remember, just like consumers in a group, if I have consumer 1, consumer 2, remember consumer had this concept of a group ID, group.id. You could call it whatever you want. Like I could say, this is ABC, just a string. Of course, you give it a name that makes more sense. But because if all of these consumer applications run with the same group ID, then they work together. They're considered, they will discover each other. They're part of the same group. So in Kafka Streams, we're not talking about, it has consumers, but what you do is when you create your Kafka Streams application, you give it something called the application ID. And if they all run with the same application ID, whatever it is, let's say X, 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 I'm just using one letter there, which is also just a string, right? Could be my app one, whatever you call it. I'm just giving an example. But when they run with the same application ID, then they work together just like consumers within a group. They work together to process the data, right? So you can run more than one instance of your application. All of these instances will run independently, but they automatically discover each other, just like consumers do when the consumers run with the same group ID. So your Kafka Streams application will discover each other if you give it the same application ID. We don't call it group ID, but it's the same concept. It's called the application ID. So in your code, it'll just be one line given the application ID. And then if one dies, guess what happens? Remember how I said the same consumer group protocol works throughout Kafka? What do you guys think if one, remember how we talked about consumers? And we talked about like if one employee doesn't come in to work today, the other employees have to do what? Oh, my audience is not with me today. They have to cover. That's right. They have to continue to process and do whatever it is. So Eric needs to cover Martin. Exactly. Martin can call in sick and Eric needs to go do. So the whole point is just like consumers, we know that that concept of rebalance occur. Well, the same protocol here with the Kafka Streams application. So if an instance die, well, guess what? The other instance will take over. And it's really, really powerful, right? And it continues to process and write it. And we'll see how it also handles the state store. So this is a very important part of Kafka Streams, very powerful. And then you might ask the question, you guys haven't asked yet, because I know most of you guys are new to this. But whenever we have people in the class who's been working with other kinds of framework like Flink or Spark, they were immediately asked the question at this point, well, what happens to the state? But this is what happens to the state. So we have the instance with the state store. Remember, those tasks have the little state store, right? I said it was RocksDB, and you're doing your processing, right? Where you're keeping track of your state. But what happens is, as you write state to the state store, it's automatically backed up into Kafka. That means in a Kafka topic. When they say changelog topic, that means typically it's a compacted topic, right? So the state is automatically backed up into Kafka, right? So if this instance fails, right, the state is not lost because I want to know how many times this user logged in or dropped out of the conference call, or how many times this IP address hit my site, how many times this error occurred in whatever, how many times this credit card was used in the last 5 minutes. All that information is here, but it's backed up in Kafka, in a special Kafka topic. So if this task dies, then another task, like it will take over, right? But when it take over, what it has to do is it will read the state from Kafka. And you say, okay, well, this sounds good. But the problem is, what if you have lots of state? Gigabytes worth of state. What if there's a lot of state? Then this process of this new task, reading a state, is going to take much longer to recover, right? So sometimes to avoid that, what Kafka does is say, look, hey, we'll allow you to have what's called the standby replica, right? So what happens is then, here's your application and here's the state store. And as this has been written, you have another instance here. And this is, let's say task one. This one becomes task one, standby. Standby for task one, right? It has its own. So as this one is writing to the Kafka topic, to the brokers, let's say in Kafka, to the topic, I'll just put your topic. This one is reading right away at the same time. So it's reading the information. So it's always up to date. So when this one dies, this can take over right away. It doesn't have to wait to go read all the data. So that's what a standby kicks in. It's like a spare, right? Or just like when you deal with, if you are a disk person, the standby, you only need one, you can have more, but the default is 0. You don't typically have a standby. Then a recover task is scheduled to an instance with a standby replica of its state immediately, right? It's nearly immediate task recovery. So standby is pretty useful. Someone says, why, right? So this is something. Now, Gang says, due to recovery process, is it possible to record, possible a record can be processed more than once? Yes, it's possible to process the record more than once. Not so much in this particular case, but actually we will show you an example of that, because when the consumer reads the data from the log, it's supposed to be able to process this data. But remember, the consumer has to commit its offset to say, hey, when I process, I need to commit. But what if I process and I fail to commit, right? If I've only committed offset number 5, but I processed up to record number 8, or let's say I've processed 3 more records beyond offset number 5, and then I fail before I commit my offset, then when a new consumer starts, they're going to go to only the last committed offset. And maybe if only I had 5, I had committed 5 before. So that means that new consumer is going to reprocess the 3 records that were already processed before. So you have to be careful with that. Okay? That's a possibility that could happen. And then now we get to this part. Windows aggregations and joins. This is so important to understand for this, right? Let's say Windows, we want to divide the streams into time buckets. We have tumbling, hopping, session, different kinds of windows. I'll talk about this in just a second. You can do joins in Kafka streams. You can join streams to tables. You can join, in this case, to say, for example, since we're working with driver location, I can join the driver location stream with the driver profile table, right? And use the criteria based on the driver ID key, where I can create an enriched record with both location and profile, right? And when you're doing joins are usually done over a window. That means you specify a time from time A to time B. So we can do aggregations, accumulate some values as new records, usually window. When you're doing aggregations, you have to specify bordering time. So when you're doing sum, count, max, min, all of those are examples of aggregations. But what we need to do is understand what window it means. How do we really use the windows? And that's so you want to know what the tumbling window, hopping window, session window is. And that's what we're about to talk about right now. So in Kafka. So remember, when I'm doing joins, especially if I'm doing streams to stream, you must be window. Everything needs to be window, right? Everything else does not have to be, but when you're doing these joins with streams, they have to be window, right? And so let's look at this example. What is a tumbling window in this case? A tumbling window just says, look, I have a fixed size. And remember, in Kafka, all time starts from January 1st, 1970, the Unix time, what they refer to as the epoch. That's the beginning of time, January 1st, 1970. Epoch. Some people say epoch. 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 Okay, so that's where the time starts from. Then now, if I say, okay, a window is saying, I could do a window that is 2 seconds, 1 second. I could say 1 week, 1 month. Of course, if I say 1 month, I need to make sure that the data has not been deleted, right? Retention policy is important. So 1 week, 1 month, whatever it is. if you have a longer time, just make sure you have the data present. But the whole point to this is a tumbler window is a fixed size. So let's just pretend that if I say I want a 5-minute window, that means my window size is over 5 minutes. 5-minute window. And let's just pretend that this time here, starting at 12:00. So that would go from 12 to 12:05, 12:05, because that's a 5-minute window. So that means any record coming in from 12 to 12:05, these circles are like records. I will use it. So if this is like, say, the number of login failures in this time, or let's say maybe this is the number of time that the user dropped out of the session, right? Or, I mean, this is going to be a lot. Let's say, let's use another one. Let's say this is the number of time a user uses his credit card. And if this credit card is greater than maybe 3 times within a 5-minute window, maybe that's fraud. So maybe I want to flag that. If this user is using a credit card, like this is maybe like I could say, how many times did the user use this credit card within this 5-minute window? So that means look at all the records coming in within a 5-minute time frame. So that means from 12 up to 12:05. They're all the red. Then I could say, okay, now I get an upper from there. That's total, maybe 8 times. But then the next window starts now from 12:05 to 12:10. It does not include the 12:10. There will be no record included in here at 12:05. This is up to 12:05, but it's not inclusive up to 12:05. So my new window starts from 12:05. I start to collect the new records coming in. So at 12:05, this is where that begins, 12:05. And then it goes all the way up to 12:10. But it will not include the 12:10. At 12:10, there would be the new start that would go from 12:10 to like 12:15. So that means this 5-minute time, I will get another result. And maybe there will be only 3 records here this time. That's okay. Then the result of that is 3. How many times I see? And then when that 5 minutes over, from this time to this time, I will no longer get any of these records. None of these records will be available to me any longer, because the tumbler window is non-overlapping. So now for this 5-minute window, I'm just getting these records, 1, 2, 3, per key. So it will not include any of these. Only these records here will be included in my aggregation or whatever I'm doing. So the tumbler window is pretty simple, I think, right? When you say a specified time, you only get the records that fall within that window. And remember, we're doing strings. If I said, for example, count the number of login failures, right? The count will never end because login failures will continue to come in. Then let's say if I keep on getting login failures, so my count will keep on increasing over time. So that's why I need to specify a border to say, okay, between this time and this time, how many failures did I get? Then I get the result here. That's the window, a border in time that you can use for your aggregations. So that's a tumbler window. Hopefully you guys are okay with that. Everybody, I'm going to look into chat right now before we move on. Do you feel comfortable? Tumbler window. Axe? No axe? Okay, awesome. So it's a fixed, so the tumbler window is a fixed period of time, and it does not overlap any records from the past or the future. If I say 5 minutes, is from that time, a 5-minute window, and it does not include the upper bound, the time at the end. So from 12 to 12:05, it was from 12 all the way up to 12:05, but does not include 12:05 because the next window begins at 12:05. And then any record coming in for the next 5 minutes, I do whatever aggregations I want to on those records, do whatever. So the tumbler window is pretty simple in that case. And you can say, maybe you want a count every 5 minutes. I want to see the average number of failures that occur in a 5-minute time, or how many times this particular user used the credit card, a giving user. If I'm doing a fraud application for fraud, I want to see how many times credit cards used within a minute. Maybe my window size is going to be 1 minute, right? 1 minute, because I want to see if I get about four for, maybe 3, 4, 5 attempts to use a credit card in a minute period, whew, fraud immediately. And maybe I then go into create and send a record to another topic called possible fraud. And then that topic will now have the user ID. And then my other microservices can kind of read this and then do something about that user. Okay, it's really, really fun stuff to think about Kafka. Then we get to hopping window. Let's look at hopping window, and then we'll take a tiny little 5-minute bio break. Okay, actually, I think this is a great point. Sorry. Let's just take a quick coffee break. We'll make it very simple. Okay, let's take a quick coffee break and maybe just like 7 minutes. I like numbers that are sort of like awkward. Or it doesn't have to be perfect. So let's just say a 7-minute bio break. 7-minute bio break. Okay. So we will resume. Simple. It's just a fixed size, right? And then we have this concept of hopping window. And hopping window is basically almost exactly like tumbler window. You have a fixed size. Let's say if I do in the same 5-minute window, but then you add something called an advance by, right? So let's say if I have a 5-minute window and I can say, okay, every minute I want to move my advance by is 1 minute, let's say. So if I say 1 minute, then what this is going to say, okay, at the end of this, like every minute, this is my advance by. So this will be like at the 6, let's say this is like 1, 2, a 5-minute window. Let's say beginning at 5 and going to 10. And then this one would be 11, right? Oops, let's just hold on 1 second. So this is 11. And then this would be like, say, the 12 and 13 and 14. I just want to go ahead and pretend here. So let's say you have these 1 minute marks. Okay. So it's a fixed size. All the records coming in at this point, 5-minute window. I want to do my aggregation, count the number of login failures, but then I want to advance by 1 minute. So when I move by 1 minute, then this window now slides up here, right? It now comes to this mark at this point, but then it will also, you slide up. So let's just say now the new window will be from year to year. So I will no longer get the records that are coming into year. These records are no longer available to me. But I have new records that are available to me. There are new records coming in year this time. And I have these older records that are still year because my window is now over this whole. So I can say this is, so every minute. So now I get my results of that, but then another minute goes by. I need to slide. So I then move on again. That's what they call this hopping window. I mean, in other frameworks like Spark, they call sliding window, very similar, but it's a tiny different. But this now, I come up, my next window, I come the year, and then that means I have to move up here, okay? So my new window goes from year to year. So I no longer get these records. These records that were here before are no longer available to me because it's out of my window time. The new window goes from year to year. So I still have some records from year. All of these are still available for my aggregation, and I have new records coming in here. So this is my new window from year to year. It's still a 5-minute window, and then it's going to slide again another minute, right? And when that minute goes by, I will no longer have these records available in my new window. And that's what happens with the hopping window. Okay, so hopping window is basically exactly like a tumbler window, except you have an advanced by. I can say, okay, make it a 1 week. A window could be 1 week, but advanced by, every so many hours, or it could be, you have flexibility to do whatever you want. So hopping window is still pretty simple, but remember, there's some overlap of records, right? There's always a chance you have some overlap of the records that are there. So any questions about hopping window? I mean, it makes sense, right? The window size is always fixed, but then you say what your advanced by. The advanced by could be 1 second. It could be 10 seconds. It could be 30 seconds. It could be 1 hour. It could be 1 week. But your window size could be, your window size, of course, if I do 1 week advanced by, maybe my window size is 1 month. Whatever you want, then you have to look in the API. And then the last one, you have the session window. I'll just talk a little bit about this. This one is good for looking at user activity. And let's say I want to see the activity, the users on the site, maybe trying to do a payment, and then maybe they walk away with, or maybe they're using a shopping cart and then they walk away. How long are they away, or how long they were clicking on the site and then maybe they went away. Now, when the user was on this site, there's a window of time I'm collecting the data, right? But I can say this period of time, the session timer, I can define this time to say, okay, I don't want the user to be away for more than 30 seconds. So if the user comes in within this defined period of time, then that user record will fall into the same window. But if the user comes outside of the 30-second window, then I have to put that user in a different window, right, by itself. So what I'm looking at is I'm looking at a key and I'm looking at the timestamp here, and timestamp. So a particular key and timestamp to determine what window the record will fall in. So let me give you an example. So let's say a record comes in here, and oops, let me clean this up a little just to make it look better. So remember, key and individual keys and timestamp. So let's look at this. Here's a record that comes in, and the timestamp says 12:00:02. And I set my session time. I say it's going to be 30 seconds. Okay. If it's within a 30-second period, it will fall into the same window. So if this record comes in with whatever customer ID and whatever the message is, and this is the timestamp. So this key, let's say, falls into that window. And then the next record comes in for the same customer ID, let's say 12:00:07. Well, from 2 to 7, that's only 5 seconds difference. That's within the 30 seconds. So that record falls into the same window. And then the same customer ID, let's say, comes in again. This was 12, a message. This one is, for example, 55. Okay, and this is the same customer ID. Now, if you look at this, from 7 to 55, right, that's greater than 30, right? That's beyond that. So you have, way more. So it's greater than the 30 seconds. That's like 37 if you subtract 37 from 55, right? There's some 40, 55. So you have 3 to 40, 10 to 50, and then 5. So 18, that's like what, 18 seconds difference. So because of that, then that record that falls in at this point, this record here, will be put in a new window. Let's just pretend it's there, this window. Okay, it does not go into the same window. And then if another record comes in, again, 12:00, let's say 56 for this given key, then that record will fall here too. And so it looks at the key and looks at the timestamp and then groups them in the window and then does an aggregation over that. And this is what a session window is. So basically, it's very, very useful for measuring like different things about users and so forth on the site. So, I mean, that's just a taste of what you need to understand for these. Windows is pretty easy to use once you look at the application. You just have to understand it a little bit and then you'll be okay. And then when we get to the Kafka Streams application, we say, okay, look at this. Configuring Kafka Streams application is pretty similar to your consumer config. I say streams config. And notice, remember how we said that you need the application ID? Just like a consumer group ID, I give it whatever ID. And then I need to specify like bootstrap servers and then specify at least, see this is saying at least 2 brokers, which is perfect. And remember, the streams application has consumers and producers. And I also mentioned that, so that means we could set consumer properties. See, like the fetch min bytes that tells the broker what's the minimum amount to send to the consumer. And then also the producer set the batch size for better throughput. Remember, you could play with those. So it's just give you, that means you can have a lot of other configurations, but this is an example of it So you have the helper class with strings. Martin says, are we skipping some records? Oh, were you talking about the one before? Oh, because you see the records could come in with any timestamp, right? So you're not necessarily skipping it, but what if that message was produced with the same timestamp? So it could come in with any timestamp. You're not skipping it, but timestamp could be whatever it is, and you would just process the message accordingly. The other question says, if there were some records there, obviously they belong to other session. Well, the thing is, you are always, when you are processing your data, you specify whatever window that you want to use. And if you're doing a session window, for example, you have a way of handling records that come in, like, because some records can be delayed. And there's a default period of number of hours to say, hey, before that record will be discarded or something like that. But you can decide how you want to handle the record if it doesn't fall within whatever session you decide to use in your session time. So this is just you defining how you want to handle messages coming in for a given key and time when you use the session window. And it's very easy to use it in your code. Once you see the example, it will make a lot of sense. But yeah, you don't have to.
I think just verbally easier. So at the light green color here, the start of the light green color is a fixed period after the 30-second cooldown, right? It could be 20 seconds, it could be 30 seconds, but it doesn't mean it's real time at the moment, is it? So the actual time could be like far on the right side. It's just that we take a 30-second pause to see if there are other messages that comes in. Is that how it works for a session?
No, sorry about that. So you're not really taking a pause. It's just saying that you're saying that within this time frame, I'm setting that 30 seconds. Let's say, for example, I'm saying this is the time I want to, the maximum allowable time in my application. I'm saying if a user has been away for more than 30 seconds, I want them to be, whatever records will come in for this given key, use it, it will be in this window, right? I don't want to keep so I'm making you make a conscious decision what that time frame, what that session is going to be, whether it's 30 seconds, 1 minute, or whatever it is. But it's not pausing, your application is still running because there's millions of records flowing in. But as you see the record, you look at the timestamp, the key, and you make a decision what window it goes into.
Let me maybe share my understanding.
Yes, please go ahead.
You can tell me it's correct or wrong. So remember, the session is always associated with the keys, right? So assuming this is a browser session, and the session key is a cookie ID or session ID, then for example, if in the first window here, window N, user is clicking here, clicking there, and every other activity is not more than 30 seconds apart, so they will be grouped under this window. And if user stop activity by pressing the home button and come back 30 seconds later, then obviously the window will time out because there's no activity. So this window will conclude. Window N will be concluded, and window N+1 will be started whenever user started clicking another button because the same session ID come again, but unfortunately break into different window, right?
Now imagine onto that. Imagine if at that time in this 30 seconds, but you have a message that arrives that has a timestamp of like 12:00 and it's 06, like with the earlier timestamp.
Yeah, I saw the lab, and I think in this case your application will can decide how to merge these two windows, right? If you choose, you can actually merge them together as the same window, but that depends on how do you implement it.
If it falls in the middle. If it falls in the middle, then there's the merge, like the session merger to you implement that. But if it still within the time, because you're looking at the timestamp, then it still will group in the appropriate window for the given time.
Yeah.
But I know that. But I love that example where you're talking about user. Actually, can you repeat that, Shirley, one more time? The first part that you mentioned.
Basically, if there's a inactivity for more than session timeouts, then then the subsequent activity will be grouped in the window n+1 instead of
Yes.
n, because they are already expired. And yeah.
Correct. So, but the thing is, you can process because you can have messages coming in out of order, right? And a message could come in at a later time, later event that can come in later, and you still want to be able to process it in the right window. And that's the thing that's sort of tricky. But I guarantee you guys, once you play with this, you will be the experts of it. And yeah. So this one is. Oh,
I saw a lab. I saw a lab. There's a good example of joining the windows. I think if you have a question, you can check the lab. Maybe you understand better after you've seen the lab.
Exactly.
Yeah, agree. It's like what Eric mentions here. So as long as, let's say now this window n+1, right? I continuously have more events on the right side coming in, so they will just be grouped together. Is it? Because it doesn't seem like the window n and the window n+1 is the same size. So there's no fixed size. That's point number one. And then let's say I have another 10 more events at the right side. They'll just be grouped together. So it's just like maintaining the WebSocket connection, is it? After like 30 seconds, there's no event, then I just break the connection. Is it something like that?
Not to my knowledge, because you see, this is always there, right? And you're basically looking at the timestamp and the giving key. And I'll try to show you guys, there's another picture. I think it will, we have in the documentation that really will help make it a little bit more clear. Yeah, I will try to get that for you guys, but it's definitely, I think it would clarify it for you as far as how you view it. And then I think were you going to say something else? I think Sharon had something else to say. Nope.
Oh yeah, I my understanding is as long as the events keep coming under the same session, then this window will keep going, right? And it's very unlikely that user will keep doing the same thing on the session. So this is typically used when in real life there's a session, right? For example, user open your app, do something, they press home, they go somewhere. Yeah. Typically, you set a timeout on those. You can break into multiple sessions.
Makes sense. Absolutely. And so you guys are, and I'm glad you guys are asking these questions. That tells me that you have a really great comprehension for this once you start playing with it. So session timeout checks the inactivity, and if inactivity session timeout, it gets grouped. Yeah. So that's the key thing, looking at the key and the timestamp. So critical components to this is just know that giving key, timestamp, and whatever your session timeout is. And that's what is using to determine what window your event is going to fall into. And yeah, typically people have difficulty understanding this part, but this is the one that you guys seem to be doing great with. So that's good. Good questions. Okay, so let's go on to this one now. It's creating a Kafka Streams application. So we start to talk about this. It's really straightforward to look at these properties. And then here now, remember, you can also use a properties file, right? Just like we saw before. And you can put the application ID, boot servers, and all of that. So, excuse me, this is a standard part of like coding, right? You have the application ID config. And remember, your application, your Streams application all have unique IDs unless if you want them to work together. And if you want them to work together, then you need to give them the same application ID, right? Yeah, awesome. So let's go on to this one now. Now, serializers and deserializers, because your Stream applications has both consumers and producers. So that means, guess what? Here's my application. I have consumers to be able to consume from the topic and bring it into my topology, right? And I have producers to be able to produce back out to Kafka topic. And we know that producers go through the process of serialization, right? And serialization, consumers have to deserialize. So we have with the Streams application, we have this concept of called the SERDES, serializer, deserializer, right? And in this case, we just say the key SERDES can be independent from the value SERDES. And there's a lot of different built-in SERDES you can use. But as you can see here, this is just showing you configuration example. Let's say here is my string SERDES. Let's say the key SERDES specify I want to use string, and then the value SERDES specify, in this case, I'm using a long. So this is just an example of showing you configuration. No. And then now, again, available SERDES, we have all of these. And you'll see this in most frameworks, you know, they're like wrappers around the default things in your framework. But yeah, we have the SerDes instead of the data type byte array, but we have like SerDes byte arrays. So these are, again, bytes wraps to Java byte and supports equality in order and semantics. Byte buffer, you have SerDes byte buffer double, you have these. So these are, again, just a standard across many kind of framework. Even in Hadoop, we have this kind of stuff as well. I mean, not wrappers around the default types. And then now this one says creating the processing topology. This is the easy part. So imagine that I have a topic in Kafka. The topic is called purchase topic, and pretend that that topic has, so I'll just say purchase topic here, right? And I have a certain number of partitions, P0, let's say P1, let's say P2. And these partitions now, of course, have data. Let's just pretend, of course. So I use the stream builder class in Kafka to instantiate. You can call the object whatever you want. Just call this builder, right? Create a builder object. And then all I have to do now, it says builder, whatever you call this, since we call it builder here, would then say builder.stream. This is how I create a stream, and to be able to stream the data from this purchase topic and bring it into, in this case, look at this picture here. I'm bringing the data from the purchase topic and I'm bringing it in to this object here called purchases. And purchases is a DSL object that is of type that is a cache, it's a cache string, right? So purchases is a DSL object that is a cache string that has the key string and the values along. And that's what's coming from the topic, the data coming from the topic, right? So the data is coming in, each record is coming in, and it's coming into my topology, but it's coming into this purchases object, which is a DSL object that is a cache string. And then I can, if I wanted to create a table, the same thing, I create my string instance of, stream builder right there. And then I say builder.table. When I say table, then I give the topic name. In this case, it will bring it into a table. Remember, the table is like the materialized view, right? And in this case, we call it the K table. So K table, so users is a K table and purchases is a string. So that's how we can create it from create a string and a topic. Does that make sense? Very simple once you look at the code, right? So you'll be bringing the data when you build your Kafka Streams application, you say, here's the topic. Then this data will be coming in through your source processor, right? Going into your topology where you'll be doing all your map, flat map, filter, all the stuff, and then producing data at some point back to some topic in Kafka, right? So it's really simple to see it this way, how to create a table and a stream, and then also to transform the data. So transforming the stream, data can be transformed using a number of different operators, right? We have map, flat map, filter, a lot of stuff. And then some operations result in K-table, some operations, let's say, for example, aggregation operation. There's a lot of things. You can go from stream to table, and there's a lot of intermediate types when you're working with streams and tables, right? But when you're using streams and tables, just remember, if you use a K-table, you can only read in from a single topic. Whereas if you're using a K-stream, you can bring in from multiple topics, right? But a K-table can only bring the data in from a single topic. But when you bring the data in, then you can do operations on it. If I have a string, right? If I'm working on a string, okay, I can do certain operations in it that will make it, intermediate. So, well, actually, let's put it this way. If I have a table and I'm working on the K-table, I can convert this to string. I can convert it to a string. And then when I have the string here, I can then do operations like group by or group by key. There's certain operations that you can do that will end up with some intermediate types where they'll call like a K group string. So imagine like I'm grouping a bunch of strings. That's how I like to tell people. Think about it. I end up with an intermediate called the K group streams. And then when I take the K group streams and I do some kind of either a aggregation or a reduce or some kind of count, I end up back to a K table, right? And then I can take a K table and do some operations on the K table, like I could do a group by, and I end up with what's called the K group table, which is an intermediate. But then when I take this K group table and do some kind of aggregation on it, right, I can end up back with the K table. So you can go from table to stream, from stream to intermediate, and then you run an aggregation, get back a K table, from K table to this, and then from this back to K table. There's a lot of different things in the API that you'll see that you could do. And we don't cover that in this class, but just know that it's really fun. So what we want to do is just look at filter. We'll look at a few of them, and then we'll wrap this up pretty soon so you guys can, let's say filter will create a new stream, K stream, by only continuing only records from the previous one. And if you look at this, so remember we created a purchases stream before, right? We used the stream builder class to create the builder object, and we said builder.stream, and we bring the data in from the purchases topic. So now we have a purchases DSL object, and we said, look, filter. And then filtering is something great to do when you're working with any kind of data, in big data, or whatever you're doing. You filter the things you don't need or change the data in some way. So I said, given the key and the value, now I'm using lambda expression, given the key and the value that we have coming in, I want you to give me just the value that has the amount less than 50. And that result will be put into another K stream. There'll be another K stream called smaller purchase. And it's a K stream called smaller purchase. So you could do filter. Filter is very powerful, very easy to use. This is an example of using filter. And of course, if this looks strange to you, it's because you probably are not familiar with the lambda expression. And some people are not necessarily familiar with it, because remember, this was added back, I think, well, in Java 8, I think is when they started to do this, if I remember correctly. Now, I was using Java up to 1.5 or Java 5, and then I started using Scala because I was working with Spark. And then I didn't do Java again until I came back to like Java 8, Java 9, like just more recently. And then, but luckily, I have been working with the functional programming language Scala. So this is perfect. If you know Scala or some functional programming, this makes life easy. So Martin said this was his favorite topic in Java. Yeah, I think by them adding this to Java, it really improved Java, because for a long time in Java 7, it was horrible. I didn't really like, before Java 8, it's just too much code to write. And Scala was becoming way more popular. This is why a lot of people went to Scala to begin with. But Java 8 brought a lot of the developers back to Java. So now we look at these things, map and map values. So if you're using a functional programming language, then map can say, look, I could take, it's like a higher order function that can accept as parameters other functions, right? So in other words, it's very powerful when you're using it in a functional programming language. But yeah, this is, look, I can use map to create a new stream, a new K stream, by transforming each element in the current stream into a different element in the new stream. Now, notice this note. Use this if you must change the key. It's a very important reason why, if you must change the key, because if I don't have to change my key, then I want to avoid using map, and I want to use map values. That means given whatever key value pair coming in the record, I want to use run this only on the values. So for example, I say, look, I have maybe a word stream coming in. I say, take the word, do a map values. And for a given value, I want you to uppercase that. And so that's what I will get. And then I will get back a K stream that is now called upper. So this is an example. I'm working on only the values portion. So remember, you could have a key and then whatever the key is, and then the value is all this data here, whatever the data is. So I say take the value and do uppercase on it. That's what I'm saying in this case. Now, what's the significance here? That the reason to tell you that use map values if you don't have to change the key. If I use map, I say, look, here's the words coming in. I want to do a map for giving key value pair coming in. I want to use this new key value to be able to change the key. So my key becomes, I say, take the value and do a lowercase on it. That becomes my new key. And then what is my new value? I say, take the value, do uppercase on it, and that becomes my new value. This is just an example showing you that you can change the key. So use the map only if you want to change the key. Now, here's the significance. And this is something we talked about more in the other class, but I think you guys are doing great with your questions. So I think it's fair to mention this. When you do something like map, it marks the string for what's called repartitioning. Yeah, the behavior is, map and flat map. So map and map values. Map value says I'm only working on the values. I don't have to change the key, right? So that's great. But when you do map says, look, I'm going to transform each element in the current stream to a different element in the new stream, and it gives you the ability to change the key. So if my key was like customer ID to begin with, CUS customer ID, maybe now I'm using the customer social security number instead as my new key, but I can decide what I want to use as my key, and I can use map to make that happen. But the problem is, when you do map, it marks the stream for repartitioning. Now, you may say, well, what does that mean? This is something that happens internally in Kafka, and you don't have to worry about it. But in most frameworks, like in Spark or MapReduce, when you're working with data and you're processing the data, at some point, you need to transfer the data across the network. This is what in Spark, we call this the shuffle. In MapReduce world, we call it the shuffle sort, right? That's when the data needs to be transferred across the network from each of those systems so that you can get your output. You shuffle the data across the network. Well, that's in Spark and in Java MapReduce. Well, in Kafka, when you have to change the key and you do a key changing operation, it marks the stream for what's called repartitioning. This is something that happens behind the scenes. So you as a developer do not have to worry about it, but that means your application has to read the data from Kafka, bring it into your, you have to write it back into Kafka in the right order, because we have to write it to the right partitions, and then we'll end up reading from that again. So this going back and forth between your application and Kafka, where Kafka will automatically create some repartitioning topic in Kafka to write the data in the right format, so you have the new key as what you want, and then it will read that data again. That going back and forth is like the shuffle in these other frameworks. So this is what the repartitioning increases. That's an extra load on the back end. Now, this happens transparently to you, but you need to understand it. If I do not need to use an operation that would change the key, then I should avoid it. Can the value be JSON object in this case? Well, yeah, your value can be anything you have in your document, and your schema, of course, will understand the format of that record. But just know that, it's just so you will know that format. But this is just this key changing operation, and then So let's see. So I just need to value. Actually, I have to look in, as long as you know the format of the data that you're working with. I have to, not, like Shailen said, I wish it was that easy. But you know what? Guess what, Martin? When you're using KSQL, it actually becomes that easy. It becomes easier to just do it, and you'll see some example of that. Okay. So but I wish it was that. I mean, it's definitely easier than using the producer consumer API, because it's just using the lambda. It's like using lambda expressions, and the more comfortable you become with it, the better. But KSQL makes it even easier, because you can do all kinds of interesting things. But so let's look at this other one: flat map and flat map values. Well, just like we saw before with flat map, remember, just like map, The only difference is flat map is something interesting. Whenever you have, let's say here's a list, A, B, C, and I have another list. Whenever you have like lists, and I want to sort of flatten those lists to say I want to create like A, B, C, D, E, F, G, H. See, I want to flatten these. I have list of lists or whatever I have, and I want to flatten it into a list. This is what that's what flat map does. Flattens a list, right? So it's very powerful. Let's say if you have a line, notice to say it creates a new K string by transforming each element in the current string into 0 or more different elements in the new string. You can modify the record keys and values using this type. So just like map, when you do flat map, the only difference is you're typically flattening some list. Like you have, imagine you have a line that says I am a line, and someone tells you, write a program to parse this line on the space or tab and make sure that each word ends up on the line by itself. I am a line. This is the kind of thing that flat map does. Now, each word is on the line by itself. So it's like you're tokenizing the line. Flat map does stuff like this. So if I have a list of lists or whatever, I can flatten the list. So flat map is pretty powerful. But when you do flat map, it's just like map. You're creating a new string, right? But you also have the ability to modify the record keys and values. So guess what? Underneath the covers, there's repartitioning. So be careful. So if I don't have to change the keys, I can say flat map values to create a new string by transforming the value of each element, the current string, to 0, 1, or different elements. That's the technical definition. And we show you an example, but the key point to note is you're working on only the value portion of your data and not the key. So it does not mark the string for repartitioning. And so this is important. This example shows you that I built the regular expression pattern that is doing on a non-word character. Capital W is a non-word character. And then I say now I have a text line string. I want to say do a flat map values. And so I take sentences and I say, what am I going to do? I want to split. Split will return an array. So I'm splitting the sentence based on the non-word character. That means spaces or tab, right? And then I will return the results into this K string that is words, where the key will be the byte offset, like the null, and then the value will be the word, basically in this case. So in this case, this is an example of flat map, but just know that, flat map values. And this is a little bit complex, showing you regular expressions. But the key point to this is flat map is pretty powerful. And if you don't need to change the key, use the flat map values instead. So it's really useful. And then we have other functions in the API, like count, really simple. I have count the number of instances of each key in the string. So I can say string. I want to do some group by first, and the group by is typically followed by aggregation function, account. So I group them together and then account, right? So we have a function called group by key and also group by. And then you also have reduce. Reduce, say, combine the values of the string. And this is just showing you samples from the API. Okay, these things there's a lot of different methods that you will have to be more comfortable with. And there's some examples we'll show you in your code, but this is just showing you samples from the API. And then Martin says, so in this syntax, array list is necessary. Well, yeah, if you're doing it with Java, yeah. I'm not sure. That's what I would use, but I'm sure there's probably some other way you could do it. And then in C#, Java, I think split auto returns a string. Now, in this case, you get back a list. Yeah, they're right. Java array and list are different. Flat map values requires a list. And when you look at let's see this. If I look at flat map values, right? Yeah, I have to look at the API. I'm sorry. Although I work with this thing, teach it. When you look at the API, you'll see all the details in there. But now look at this one, group by and group by key. So look at this, guys. let me give you an example. Imagine you have zip codes like 902, let's see here, 90210. That's like Beverly Hills, 90210. And let's say the price, this is like the zip code. And this is like the price, home, in other words, price of homes. And let's say this in millions. So I have like 8 million. And then I have another reading that comes in. Maybe this is an application sending the sales of the home. And I have another home sold for 10 million. And then I have 90210 gets another home sold for 12 million. And then I have like 90310 comes in for like 10 million. And then let's say 90315 comes in for 2 million, something like this. So if I have this kind of data coming in and I do something like group by key, where this is the key, zip code is the key. So I say whatever the key is the same, group by key, group all the values together. So let's say we take the 90210 as the key. So it will look like this, 90210, that's the key. So I will group the 8 million and I need the 10 million and I need the 12 million. So it's an 8 and a 10 and a 12. And then this one will be 90310, that's the key. And then here's the value 10 million. And then this one 90315 is the value 2 million. So after I do my group by key, I typically want to follow by some aggregation. In this case, if I did a sum, then I can add up the total of all the sales, right? That's it. That's for 90210. Then my final aggregation or sum, sorry, we're getting like 30 million for that. And then this will be 10 million. This would be 2 million. But the group by key, hopefully that makes sense. Like where the key is the same, you group all the values together, all the data associated with that. And then you can follow by reduce function to do whatever you want to do. Okay. So it's really, really interesting. And then here's the sort of circle. This you'll see in our documentation. I can go from streams. I can do map filter joins on streams to stream. But when I have a bunch of streams, I can do like reduce aggregation on the stream. In other words, I have like a K group string. And then when I do a reduce or aggregation, I end up with a K table. And then I can do like map values, filter, join. But then if I take a K table, I need to convert the K table to a string. That would give me a K string. And if I want to write out to a topic, I need to convert the table to a string first before I can write to a topic. So remember, you have to convert your string before you can write to a topic. Okay. So let's go. Again, this is just a snippet. I'm going a little bit more than normal, but writing streams back to Kafka. So streams usually terminate by producing back to Kafka, right? So there's a method, the actual method TO is a method TO. That's a method to say, look, take whatever my stream is, whatever your stream is, and write it to some topic here. So TO is very useful to be able to do that, right? And just to let you know. And then, of course, like any other framework, we want to give you ways to look inside of the frame, right? Useful. So especially when testing and debugging, you can do a print and look at the information. And that part is pretty simple. Let's look at this one. Running the application, you always have to start, right? And you have to, so start processing the stream, you create your K streams, object, configure it using stream builder, then you call start. Okay? So it becomes like boilerplate code. You do it over and over. It becomes really standard in this part. And then shutdown, you always want to shut down. And there's some people would show you different ways of shutting down your application. But after the application stopped, then Kafka will migrate, like I say, any of the tasks that you have, if those tasks have been running for some time, right? It will migrate them to other instances that are available. And if there's no instances, then of course that's the end. But you want to add a shutdown. So you need to make sure you shut down your application, graceful shutdown. And then sizing and scaling for Kafka streams, very important. Remember, every task has a state store, uses RocksDB. It's very fast. RocksDB will write to disk. But just like Kafka, remember how we talked about Kafka has a page cache? Well, RocksDB keeps a lot of things in memory, and then it will eventually write to the disk. but it makes it fast because you're writing to memory lots of time before it goes to disk. So, but because of that, you need to use disk space because it needs to write to disk eventually. So the state stores have like 50 to 100 megabyte memory overhead, because remember, it's writing to memory first before it gets a disk. Clients persist the state store to resolve this, like the Kafka topic those state stores for the task will eventually be written. As you write the state is written to the Kafka topic, right? And so if the client state store fails, then the data is recoverable. We saw that. We talked about standby. Now, this is important part to see if the client performance is really CPU bound, right? Then you want to have more cores in whatever containers or VM or systems you use. You want to, and because of that, you might want to also, if you have more cores, you can increase the threads. And it's just a simple property to say num-string threads to increase the number of threads. The default is one thread, right? And if the client performance is bound by network, right, memory or disk, so I have a lot of I/O activity, or I see a lot of network go, right? Memory or disk, then I want to scale out the client in this case to avoid saturation of network or put no drain on the memory or avoiding a lot of I/O. So you want to spread them out across. So in other words, when you're working with the stream applications, you can scale up or you can scale out by having many more containers or instances to run your Kafka Streams application. Remember, these are not brokers that we are talking about. They're Kafka Streams application. Okay. And then Kafka Streams, for example, last part to show you a simple example. The example actually is really, it's so much easier to look at. I have my Streams application, very simple, like standard Java, public class name, public static void main, right? Standard Java. I have my properties that I create. Notice I'm giving it streams, using streams config to give it an application ID. And then I'm specifying the brokers that I need to connect to. And then I'm also now looking, in this case, I'm using some of the consumer property to say, look, auto offset reset config to the earliest. Well, what this is saying is, what can I do when I don't have a valid offset? You get a choice. That means you can't get the valid offset. You want to start from the earliest, or you want to start from the latest, or do you want to fail, or, not whatever. So in this case, you're saying, look, I want to start from the earliest. Then I say, look, I specify my key 30 and then my value 30. So very standard, no big deal. And then here now is the part where this is where you have to know, be familiar with DSL. So at this part, I use the stream builder class, instantiate my builder object. And then notice I say builder.stream. I say, yeah, bring the data from this text lines topic, bring it into my text line object, right? Which is a K-stream. It's a DSL object that is now a K-stream, where you have like using a byte array, because maybe it's just words in the file, like sentences. So you don't have a key specified. So this is like the null, or like what you guys saw in the first exercise that you did. So it's just use the byte array, and then the rest here, the value here, it's the string in this case. So then I say, look, take this text line DSL object that is a K-stream and do a map values on it. Work only the value portion, take the value and do an uppercase on it. And that's going to return this K-stream that is also uppercase with map values, right? So now I have an uppercase word, okay? Then I say, now take this uppercase word, and I don't have to do them on separate lines. I could have just joined them all together with a dot, but we're doing this here to show you. So take the uppercase map value and use the method TO to write it out to a Kafka topic. And then I run the streams application with start, right? I pass the configuration, and then I go ahead and add my shutdown hook, right? So this is very, 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 very straightforward. And then here's with stateful processing, an example of stateful processing. All of this is the same application ID, all of this, streams config. I say the key 30 byte array, value, string, no problem. And then here I start my string build, instantiate my builder object. I said builder.string, bring the data from the text line topic into text lines, which is a KString DSL object. Then I said take the text line DSL object and do a flat map on the values from the given values coming in. I want you to split at a non-word character and then do a to lowercase. And that's going to come into my word counts, which is a K table. But before that, I'm not done yet. Then I say group by, given a key and a word, I want to group by the word. So I'm specifying, I'm changing. Group by is one of those functions. If I don't have to change the key, I use the group by key. In this case, I'm saying, look, given a key and a word, I want to be able to do by word. So I'm using a group by, I need to specify this. And then I do a count. I say that count. I'm using a materialize as a helper class to write the results to a state store, right? And to write it out to the state store. But all of that gives me back this K table. So the K table now has a string and a long. And then what I'll do is take that word counts and convert it to a string because I want to write it out to a topic. So I need to convert the table, which word counts as a table right here. I convert it to a string and then use the method TO to write it out to the topics and specify the string and a long. This is really, really cool. Kafka does only understand byte array for both key and value. That is correct. Because remember, when you do the serialization, that's all that goes in there. It's only the byte array. And then, so even with simple string, you need a SERDES. Yep. Remember, when producers produce the data, they're sending it, you go through serialization, partitioning, and batching, but you send that to Kafka. Kafka only understands those bytes. And so this is, let's go on to this. And then now, here's the topology part. It says, look, this is just the last part. You say, what do I need to do? Well, at this point, build the topology and run the stream application. And that's what you do right there. So, and then I pass my config and then go ahead and, of course, add your shutdown hook at the end. So we added some other detail to you, but in the essence of time, we're at this last part. When you want to join the stream, let's say you can enrich records by doing join. Very simple to do join in Kafka streams. So in other words, remember, we need to specify a border in time to do joins. We need the window, right? Joins need to be window. So remember, if I have like a.join b, this is considered to be the left-hand side, and this is considered to be the right-hand side because it's on the right-hand side of the join. So left-hand side, right-hand side. So in Kafka, you can do the left join, the inner join. You can do outer join. There is no right join in Kafka, right? So this just shows you an example where I say, look, take the string, whatever string you have, and dot join to another string. That's like saying a dot join b. So I'm saying whatever this string is, dot join with this other string. And then you have this concept of a value joiner. What is the joining criteria, right? And this is just saying, well, in this case, given the left value and the right value, I want you to just do stuff with the left value and right value. In other words, you can have some method that does something specific. And that's what you're specifying how your join criteria should work. But it's really simple to do a join in Kafka streams. And you specify the duration of time in minutes, 5 minutes. That is your window size, right? The join window. So this is, again, like your window, it's going over time. And this join needs to happen in this window. And we gave you some other information about this. But remember, guys, we're giving you an example of these things. So that do stuff you have is like your value joiner, right? So you have, again, this is very important, but we don't have. So this is just an example here. And then we come to this one, Kafka Streams Processing Guarantees. It supports at least once with no failures to say we'll process data exactly once. We can, if you want to use exactly once processing in Kafka, All you have to do is set this property, processing guarantee, set to exactly once. The default is at least once. Some people would ask, well, how come Kafka doesn't just set it to exactly once? Exactly once does add a little bit of overhead, right? But just know then there's also some changes a little bit to the API. So the default is still at least once, but if you want to do exactly once processing, it's there. You can make that happen. And then more Kafka Streams API features. Know that it's in the documentation. It's a check the documentation, sign up for the training. It's a 3-day class. And that brings us to this point where it's now great. So I tell you this, here's the format. We are done with this. That's a great lab. And I don't expect to give you homework because I know people have families and have obligations. So I will give you up to 8:30 a.m. tomorrow morning to say that I'm giving you some time